Welcome to the Game Dev Pantry, a series where we retro-engineer interesting mechanics in Unreal Engine 4. Don't forget that you can always grab the projects we make by following the GitHub link in the description. The company From Software has been making games since the early 90s, but really made its mark on the North American market with Dark Souls, by masterfully blending action RPG elements and the Metroidvania level structure. The interconnectivity of its many areas, the unique experience system, as well as the mastery required to play, charmed the hardcore player community and paved the way for an entire series of games based on these principles. This would ultimately lead to their last opus, Sekiro Shadows Die Twice. This game takes root in the Soul genre, but also builds on other inspirations, which could be narrowed down to two other franchises, Tenchu and Otogi. While having bought the rights to the Tenchu franchise and publishing most of its games, From Software only personally worked on the ports for the PSP. However, it is still clear that Sekiro's draws inspiration from this series. Tenchu was first and foremost a stealth game, in which you played ninjas. One of its strengths as a stealth game was that it used verticality as a way to give the player vantage points and safe spots, not unlike the Arkham series, only 6 years earlier. And one of the tools that the ninjas had access to was, you guessed it, a grappling hook. While a bit crude and a lot less satisfying to use, this mechanic opened up a whole world of possibilities for the player. On the other hand, there's Otogi, a series entirely developed by From Software. While critically acclaimed, these games did not sell well, which is why you might have no idea what we're talking about. However, we think that it really inspired Sekiro's world building and storytelling. In Otogi, you play a powerful warrior brought back from the dead by a princess to break a curse that is filling Japan with demons. Sounds familiar?
None shall pass.
Otogi drew clear inspiration from traditional Japanese mythology for its levels, enemies, and overall sound signature, and so did Sekiro. While still keeping its Souls identity, we think Sekiro is a love letter to both of these franchises. It's now time to reproduce the grappling hook in Unreal Engine, but first, let's talk about Sekiro's dynamics. Unlike other Souls protagonists, Sekiro's main character, Wolf, has a lot of vertical movement options. He has a dedicated jump button, with which he can wall jump, and he has, of course, the famed grappling hook. Whereas other Souls games only used verticality in the form of ladders and elevators to create shortcuts and more interesting level design, Sekiro also incorporates this verticality in its combat with jump attacks and counters that allow for even more extravagant level design, and this all leads up to far more interesting navigation challenges. The verticality is also key to the stealth part of the game. It is used to sneak up on enemies, execute them with jump attacks, or get better vantage points to plan your offensive. It is even used to easily escape from a fight to restore your health. Therefore, the grappling hook is not only a versatile movement option, but it is also a core element of every part of the game, may it be stealth, navigation, or even combat. Now, let's take a closer look at our video's main objective. The grappling hook in Sekiro can only latch to specific points. We'll call those grapple points. These points are detected in a certain range and are shown as a node in the user interface. A point that is visible in the UI doesn't mean that it can be used yet, though. It simply tells the player their best option. The game only shows one grapple point at a time to avoid visual clutter. Only the point that is the closest to the center of the player's point of view will be shown. In other words, the game tells you what point is closest to where you're looking at in order to facilitate snap decision making. The node will also show how close you are to it by filling itself and eventually turning green, indicating that it can be used. So before we start coding the actual grapple mechanic, we'll have to create the grapple points and the detection system. We will start with a third-person template, because it has the basic movement and animation for our project. Once that's done, we will create an actor blueprint that will contain all the grapple points logic. The root will be a sphere static mesh that will be used for detection purposes later. After that, let's open the third-person character blueprint and adjust a few things. Let's clean it first to keep only what we need, and then adjust the gravity and camera so it feels more like Sekiro. Then, we'll create a function to detect surrounding grapple points in a specific range. For that, we'll use a multi-sphere trace for objects, and set up a specific object type for our grapple points, so that our sphere cast only detects the grapple point actors. We'll set the range to 2000 units, and promote it to a variable. This function will fire every tick to ensure a tight response. Now that our grapple points can be detected, we'll set up the node UI in order for the player to have a feedback. We'll create a new widget blueprint and call it Detection Node. Then, we'll take two images of circle and put one as the node background and the other as the fill component. Once that's done, we'll go back to our grapple point and set up the widget. Add a widget component and set its class to the one we just created. Let's create a reference to the user widget object to access the widget properties later. We then need to manage visibility for these nodes. So let's do this using two functions, activate and deactivate. These functions will be called to show and hide the nodes, as well as reduce performance cost of nodes that are too far away. We'll also use these functions to feed them the player reference, so we can access it later. Once these are created, we'll make a function that calculates the distance from the player and modulate the size of the filling component to notify the player of how close they are to being able to use the grappling hook. We'll use a map range clamp node to translate the player distance to a specific size for our filling component. The range will be determined by two variables in the player. The first being the detection radius of the sphere cast, which we set up earlier, and the second, a smaller value, indicating that the player is close enough to use the grappling hook. Now if we plug our function to activate the grapple points, we have a problem. It activates all the point with no way of deactivating them yet. We'll add a few things to our function to correct this. We want it to only activate one node at a time, the one closest to our camera's center. To do this, we'll instance a for each loop. For each grapple point detected, we'll take our camera's forward vector and the direction from our character to the grapple point. We'll calculate the dot product of these values to find the angle between those vectors. A dot product of 1 would mean that the vectors are exactly the same, while a dot product of 0 would mean that they are perpendicular. For nodes to be in screen range, we want the dot product to be higher than 0.7 approximately. So before the loop, we'll set a variable called highest dot product to 0.7. This will be our smallest possible dot product, since a dot product smaller than this would mean that the node is out of sight. Therefore, we'll compare every dot product to this variable. If it is higher than the variable highest dot product, we'll save it as the new highest dot product. We'll save a reference to the grapple point as an actor and cast it later when necessary. Basically what we have is a loop that finds the node closest to the camera center and keeps the grapple point as an actor reference. We'll create a new function that will be called at the end of the loop. The function will check if the loop created a grapple point reference, meaning that if all the nodes were out of sight, we have no nodes to activate. The thing is, as it is, we could detect nodes through wall or other meshes, and we don't want that. To make sure that we have a line of sight to the grapple point, we'll use the detection sphere mesh we set up earlier. What we'll do is a line trace from the camera to the grapple point using the visibility channel, and check if the hit actor is our grapple point reference. Then, and only then, will we cast the detected actor and create a new variable called grapple point ref. To make sure that we don't detect the same point and cast it again, we'll always make sure that first the new detected actor is not our current grapple point. Once all of that is dealt with, we'll finally activate the grapple point through the function we created earlier. So now we have it, a function that will make the right node appear. However, it does not remove past nodes, yet. We'll create a new function called deactivate grapple point ref. Basically, this function will, as the name implies, deactivate past grapple points. In this function, we'll always make sure there's actually a reference to past grapple to avoid null pointers. Then, we'll deactivate the node and set this grapple point ref to none. We'll call this function on many occasions. First, when there are no nodes in range, or when there are no nodes in sight. We also want to call it if the line trace detects something in between the camera and the grapple point. And finally, we'll add it right after the cast to make sure that before adding a new one, we remove the past one. That's almost it for the node detection. The only thing that is left is to set up a component in the grapple point to make sure that the player can't grapple from too close, or if they're on the same level. At first we thought the developers had strict rules for this part of the system, but with further analysis, we discovered that these rules could change depending on the level design, meaning that it had to be something more flexible that could be adjusted by the level designers. The rules were not absolute and were handcrafted for each node. What we did is set up a volume that, when entered by the player, deactivates the collision of the detection component, and then re-enables it when the player leaves the volume. This way, we can set up rules that suit the level design. From Software usually lets the character animation dictate the pacing of movement and attacks in gameplay. As a result, you won't find instances of animation cancelling in a Souls game. Sekiro follows suit with the grappling animation. For us, this means that instead of the code dictating how the animation behaves, the animation will dictate the timing and the variables the code works with. We'll use the animation notify at specific points of the animation to fire specific functions. But before we use animations, we need to create some. Unreal Engine 4.25 added new features to its control rig, making it a lot easier to use. It is more streamlined and way more practical, but unfortunately, there's no official documentation or tutorial regarding the 4.25 version at the time we made this video. So we decided to provide one for you, based on what we managed to figure out on our own. The Control Rig tool allows the user to set up controllers to an already rigged character directly in the engine, so the user can animate their character in a level. This is super useful for a number of reasons, notably animating with props, or even with the help of the construction script, using other Control Rig characters to do interactions, or just to see what your model and animations would look like in your level with post-process and lighting. This tool has the potential to largely improve the workflow for animators. So with the help of the only online resource we found, a guide written in Japanese, we proceeded to set up our control rig for the basic Unreal character. For this you'll want to enable the plugin first so that you can actually use the control rig features. Note that the control rig plugin is not considered production ready. However, since the tools create animation assets, you can simply remove the plugin and control rig afterwards to build your game normally. After a quick restart, you'll be ready to go, and you can create a control rig class. Setting up a control rig in Unreal is really similar to other 3D engines, but worry not, we'll take you through it. First of all, you'll need to import the mannequin hierarchy. Once that's done, we will start setting up controllers. Controllers are used to modify bones location, rotations, and even scale. They are basically what allows you to animate a rigged character. You'll always need to adapt your controller to your project's needs and personal liking. So this is just a possible version of what a control rig can be. We always need to set up a root controller that will be parent to all our other controllers. We'll then proceed to create a hips, spine, and head controller. We'll create 3 spine controllers with different levels for each children of the hips and lower vertebrae. We can assign their initial transform by dragging them close to the bone we want to control, and by using the set initial transform from closest bone function. Once our controllers are in position, we want them to actually influence the bones. To do this, we'll modify the bones transform in the rig graph using the controller's transform. Though we want to be able to move the hips, we only want the other controllers to change bone rotation, so we'll lock translation using the limit setting. We'll then set up our arm's IK. IK, or inverse kinematics, is a process in 3D that allows bone position and rotation to be adjusted naturally like a chain, granting the animator a puppet-like control over characters. For the arm, we'll create a hand controller and also a pole vector controller to better visualize our elbow control. We then set up the IK from the upper arm to the lower arm and using the hand as an effector bone. The effector bone will control the whole IK using the pole vector as the rotation direction. We then set up the primary axis, which is the axis the IK works on relative to the effector bone axis. The secondary axis is mainly used for rotation directions and will orient how the pole vector affects the rest of the IK. Finally, we'll want our pole vectors to always stay close to our elbow so that they are easily accessible and offer direct control over elbows. It is important that we execute this part after the IK is executed though. The legs IK work exactly the same, except that we'll use the thigh as bone A and the calf as bone B, and the foot as effector. We're almost done. The last thing we want is control over the fingers. We specifically want to be able to open and close our hand. We'll set up a control that will allow us to manipulate all fingers of the hand at once. Using the distribute rotation node, we'll set up each finger individually to react to the translation of our controller. The controller will then be locked between 0 and -30 on its y-axis, and will serve as an alpha value. The interpolate node will interpolate between distributing a rotation of 0 to 60 on the z-axis, depending on the controller. If the controller is all the way up, the hand is open, and if it's all the way down, the hand is closed. So that's it for our control rig. Now that our control rig is done, we can start creating the animations for our skeletal mesh. Dragging a control rig in this scene will automatically create a level sequencer which we can use to create animation keys. Using control rig, we have to make sure to animate our character at a location of 0, 0, 0 in our map. When exporting an animation, we'll always need to manually save it and reload it in the content browser if we want to open it right away. And that's pretty much all we need to know to start using the control rig. There are a lot of different grapple animations in Sekiro. However, for the purposes of this video, it would be counterproductive to reproduce each and every one of them. So we will focus on the two possible states in which Wolf can grapple, from the ground and from the air. So what we did is, for each state, we took our preferred animation and reproduced it frame by frame to get the timings right. Note that we will be aiming to get the timing right. We in no way intended to reach the level of polish Sekiro has in its animation. If you're interested in learning more about animation and game animations, we put down a few links in the description that goes more in depth. In order to provide a better back and forth between polishing our animations and implementing notifies, we created animation montages that contain all the notify data. This way, when we change the animation inside the montage, all the data stays the same, improving our workflow. Once our montages are created, we insert notifies at targeted frames to trigger specific behaviors. All animation notifies can be called in the animation blueprint. We created a corresponding function in the player pawn that will fire code when called from the animation blueprint. Once our notifies are set up, we want to be able to fire the grapple animation using our node detection system. First of all, we always make sure we have a grapple point reference, and then we make sure that we are in grappling range of it. After that, we take our grapple point reference and save it as a variable to make sure that if we look at another node while grappling, we still have a reference to our current grapple point somewhere. Then, we need to save a destination vector. However, we don't want this destination to be exactly the grapple point, as we don't want our character to stop there. We want the grapple point to have a landing zone. We'll quickly create a mesh using geometry brushes, and then generate a collision using the mesh editor. Then we're gonna add this platform to the grapple point blueprint. Let's go back to our pawn. Now that we have a destination vector, we will need to offset it to take into consideration the capsule size of our pawn. We will instantly rotate our character to look at our grapple point and finally fire the animation corresponding to our character's state. Before coding our grappling movement, we will create a small animation for our nodes. When we activate the hook, the node will expand and disappear. After a delay, it will reactivate itself and reappear. We will call this function just before calling the animations in the pawn. Using a boolean, we'll make sure that the grapple point does not fire unnecessary code while it's being used. With this done, we can finally start our grappling movement. Basically, we want to interpolate the pawn's position between its starting position and the destination we established earlier. The movement starts only when the animation reaches the point where the pawn pulls the rope. At this moment in time, we will remove gravity, stop the player movement, and set the starting position for the movement function, and also set the character movement mode to falling. We will create a boolean to track if we are moving with the grapple, and activate it at the specific moment. On tick, if the boolean is true, we will fire our grappling movement function. We want our movement to be specifically linked to our animations. We want our player to travel a distance between specific animation times. Using our animation montage position, we will be able to map the frame times to an alpha value that is used for interpolation. This works great, except that the interpolation is linear and feels terrible. To improve game feel, we'll use curves to further map animation time to position. We made our curves so that the speed is faster at first and then slows down afterwards, not unlike an inverse square. We'll also need to add a height offset to the translation so that the pawn lands from a higher position. We'll use another curve to implement this effect, mapping animation time to a height offset value. Then, we'll make sure the player can't input jumps or movement during the whole grappling animation. Using a boolean, we will gate those specific inputs. Using an animation notify, we will re-enable input at the end of the animation. Finally, to make sure the character doesn't completely stop for the first part of the animation, while chain grappling, we implemented a launch to give a feeling of momentum. The only thing left to figure out is the rope visuals. We will simulate the rope through a cable component in the character. The cable end will be attached to a static mesh component to give the end of the rope a distinct visual. The rope visibility will be managed through animation notifies, while its length and location will be managed by curves. We want the rope to shrink and move to give it a sense of physicality. So by using curves to map animation time to location and rope length, we are able to stretch the rope to give it a feeling of tension, to throw it, or to wind it up. We'll have to save the distance between the pawn and the grapple point as a variable that we'll call rope base length. To change the rope tension, we will multiply the rope base length by a ratio that we mapped in our curves and set our rope's length to that value. By tweaking our curves for each animation, we ended up with a result that looks like this. For the final touch, we took the grapple throw and swoosh sounds from Sekiro and added them to our pawn. Then, using a few grapple points and geometry brushes, we built this level to showcase a bit of our gameplay. Thank you so much for watching the video. If you enjoyed our content, please give us a like and subscribe to see more. If you have questions, feel free to ask in the comments section, and don't forget that you can always grab the project by following the link in the description. Thank you, and have a good one.